Okay, are we recording on the right mic? I assume we are. I don't know. Wait a minute. That just turns the mic off. All right, I'll have to take this part out later. Hopefully the mic is recording correctly. Hello. Okay. This is a guide to aerosol flows from the nose and mouth during speaking, breathing, coughing, sneezing. This is a very complicated area. I'm just giving you one little piece of my area of study, which is the particulate distributions and the flow. Okay. So I drew up these little pictures so we can look at the different activities at work. Let me see, I probably held up the, okay. We'll start with an easy one. So we start easy and get kind of more complicated. So the easiest one would probably be breathing. All right, with breathing, so here's one guy, here's the other guy, a little mouth. Okay, so you can see with breathing, we do have some interaction between these plumes from a distance. Now, the distance between these is not necessarily to scale. That's more of a demonstration of what's happening. They could be closer, they could be farther away relative to the scale of their heads. However, that gives you a reasonable indication of what happens to the wavefront from the breathing, these phonons, and the air and the aerosol plume that's coming from this guy, as opposed to coming from this girl, and how they meet in the center and how they interact. They do interact, however, the flow is relatively laminar. The Stokes flow is usually, with normal breathing, not quite up into the transitional domain, so approximately Reynolds numbers are less than about 2,000 if memory serves. The walls of the air passage are essentially infinite, so you have a Gaussian drop-off at the edges, and it prevents, you have items in the room. For instance, the other that will complicate things. If somebody's in a room, you'll have a lamp next to their bed, and that essentially acts as a type of a waveguide. However, from the theoretical model, we don't look at any of that. We just assume that it falls off infinitely far from their face, and you have the airflow that can move in any direction, and the barriers are the other person, and that's all. So you can see what happens, just a typical type of breathing exchange. They interfere with each other like that. Okay. So that would be a simple case scenario, laminar flow. Now, what happens during speech? Okay, well, let's take the simpler one first. In physics, we always got to start simple and go complicated. Okay, so here is the simplest case of speech. All right, this could even be applied to like a mild cough, for instance. Okay, so you can see there's the person in the middle, there's the cough coming out of their mouth, and you have no other barrier. Okay, I'll show you this one later, but you can see we have that other barrier. The other barrier is the other person. From an epidemiological point of view, that's obviously critical because that's the person who gets infected, or that's the person who gets the benefit of the other person's bacterial stream, or that's the person that gets a piece of pizza on their chin because the other person was telling them a joke in an Italian restaurant, and it made them laugh so hard that they accidentally coughed out a piece of pizza. Okay, all of these things in life, but we're not looking at the second one yet. Just look at the first one. So here's the person, all right? And we have a laminar flow mostly. You can see what happens here. Laminar flow mostly coming out, but it begins to grow turbulent. And part of the reason it grows turbulent is because speech is modulated. We have words. We don't just talk like this. It wouldn't make any sense. We wouldn't know what anybody's saying unless we had like one word. But we have a lot of different words, and that's punctuated. We have gutturals. We have stops in our speech and starts in our speech, and we speed our voice up and we slow it down, and it gets louder and it gets softer. There's all these modulations in our voice that create that turbulent flow. They transition that regime from laminar up to transitional and into turbulent. So essentially, even though we don't have barriers on one side, the ability of the particles to move laterally through the flow is restricted somewhat by the viscosity of the fluid. In this case, the fluid is air. So while we don't have walls, we do have a characteristic time that these particles can move laterally through the flow. All right, that essentially creates a barrier. In creating that barrier, you now have a Stokes flow, and you're able to compute what the Reynolds number is of that system. And then during normal speech, as we speak, the Reynolds number of that system, of that tube of speech and air and spittle and whatever it is that we're speaking down that tube, can be characterized by the Stokes flow. All right, so as we speak, we have this variation. It goes from laminar to turbulent and transitional. It may not even get into turbulent that often, depending on who's speaking and the temperature of the air, which affects the viscosity. We all know that cold air has the ability to transmit some pathogens even better than warm air. And part of that may have to do with viscosity of the air and tunneling that material. You can see, for instance, when you breathe, if it's a warm day out and you have some ice cream in your mouth and you breathe out, you'll see you get that smoke. It's the same type, although on a much smaller scale, of breathing outside on a very cold day, and then you have the condensation from your breath, making that smoke cloud, right? Not smoke, but that small cloud. So you breathe out clouds. That's part of the effect. You can actually see the difference on a hot day versus a cold day. On a hot day, when you have ice cream in your mouth and you breathe out, you'll look at that much smaller plume, but you'll see how it spreads differently than the cold plume does in the winter. Look at the difference, the way they spread. The viscosity of the air changes. Generally, as a fluid heats up, the viscosity decreases. So a warmer fluid, for instance, the air on a hot day, would have a lower viscosity, and then you would see a different Stokes flow. Okay, so this is where we are. We're at a laminar flow usually, and as they speak, it starts creating all of these turbulence patterns. Okay, the turbulence patterns can do all kinds of things. They can create unpredictable results with pathogens coming out of the mouth. They can create unpredictable results with breaking apart of water droplets. There's all kinds of things that can happen. If you've ever seen that cliche of an opera singer singing, oh, and then the glasses shatter, right? That has proved. I mean, there's been actual opera singers that can hit a certain note. Maybe it's just an urban legend. I think it's true. As far as I know, it's true that there have been opera singers who've been able to break fine crystal, but with their voices by vibrating it fast enough that it's able to crack. Okay, so these things are real. Normal speech and voice and screaming and yelling and all the other stuff can create sufficient turbulence to be able to alter the characteristics of particles. Okay, how much? Maybe not so much on a nanometer scale. It might be, for instance, slightly changing the hydration radius, or possibly breaking apart some larger water droplets. I mean, we'd have to do some work to see about that, but okay. So now you go to the slightly more complicated situation. So now you have speech, all right, with two people. So now that person is a barrier for that person, and this person is a barrier for that person. Okay, so as they speak, you can see we have roughly a laminar flow, but this is what's important, okay? Somewhere midway between that conversation, we have destructive wave fronts and constructive wave fronts, okay? And what happens with those wave fronts is that we have a different kind of effect. So it becomes more complicated than this. This becomes more complicated. This is a two-body, well, it's far more than a two-body problem, but as it's simplified down to its base assumptions, it's a two-body problem, thermodynamically speaking, at least. Now, you'll notice as I go through these, I don't have any with three heads. I think I might have one or two. And the reason for that is a three-body problem is out of our ability to calculate these things, even to illustrate it with simple diagrams like this. Three-body problems are, from a physics perspective, somewhat unsolvable. There's ab initio ways of approaching them, and you can make estimations and all this, but we can't really solve three-body problems in a closed form. They're just too complicated. Okay, so we have this linear transition, all right, construction interference during normal speech. Well, what happens now, let's get a little more complicated still. We're going to bump up, let me see, which one have I shown? I've shown that one and that one. Okay, so now we're going to bump up the velocity of the air coming out, And let's go to, from a simple voice to say, a cough. Okay. Now, a cough is essentially super speech. Yeah. Because super speech, like if I say, get the ball, grab the thing. Okay. I'm, from a turbulence perspective, the sharp things that I'm doing are putting more air onto the space. They're increasing the entropy of the space more quickly. Is there a dog in here? There's a dog in here. I heard a dog. Hey, doggy. All right. So they're increasing the entropy of the air more quickly. So for instance, right, or get, that increases the air. That increases the entropy more quickly because I'm putting more air into the space in a shorter time. Okay, than if I were to say something like slow. So you can hear that the modulation of air is going to be very different. In the case of slow, I'm allowing the air from my chest to go into this space very gently, keep it more in a laminar flow, whereas the thing get, I'm taking more air and I'm releasing it more quickly. So a cough is essentially super speech. A cough is getting that much air out of your lungs and out of your chest that much quicker, and it makes that much more. It changes the entropy of the system that much quicker. Okay, so we have a mild cough, and now what happens is we start seeing these bands. All right, we have a laminar flow that is being quickly interrupted by a transitional to turbulent flow. All right, so I guess this is a hard thing to describe, but I guess you might say that it's like a scar. It's like a scar in that where these rings are, the transition was so quick that in some cases, like snapping a whip is a great example. When you snap a whip, that's a fantastic example. When you snap a whip, you're exceeding the speed of sound for the tip of that thing. And if you snap it enough, you can supposedly, and I think I verified this at one point, smell some of that ozone type smell. You're actually adding so much energy to the system that you're potentially binding or breaking apart oxygen molecules, O2s, and some of them will recombine into O3s, which you can smell, and you can smell them as they come out of a laser printer, for instance. You're breaking apart oxygen molecules and you're reforming them, in some cases, into O3, which is toxic, which is tropospheric ozone. Cars do this all the time. It's a form of air pollution. We don't want too much of it. Small amounts of it may be helpful. I don't know. That's outside of my area of expertise. But large amounts of it are clearly harmful and clearly damaging to lung tissue. And that's what this is. It's a scar. Okay, so as you add energy to the system quickly, you sometimes can create an effect. Now, in this case, it's not enough energy to create ozone. I think that's really, really unlikely. Maybe a tail end distribution, tail end distribution. Okay, if that. If somebody's screaming at the top of their lungs, maybe they'll get a tail end distribution of ozone made. I don't even know if it's possible, but it's something that it's like at the most I can imagine it only be a tail end distribution. Okay, if it's possible at all. So, however, thermodynamically, you have these quick changes to the system, and it will leave these marks, which you can detect. You can measure them. Now, as you move up from a cough, say we have a more violent cough. Okay, so by this point, those distributions have already moved far away because you've added sufficient amount of energy to the system that they then push them out. All right. Now, what's even more violent than a cough is probably a sneeze, and that's when you get this. Okay, there you have rapid aerosolization. Okay, because in that case, what happens is and this is why I suspect it's bimodal distribution, because bimodal distribution is an effect of splintering or fracturing and an effect of precipitation or aggregation. Small, tiny particles in the air accumulating to a point where they can't accumulate much larger. depending on their surface energy, that would be there. That's the chemical composition of them, the impurities in the water, the whatever other microbial and elemental effects our body might give to our saliva and to our snot and to the water particles in our lungs. I'm sure it requires some impurities down there from the air pollution that comes up. But anyway, that whole structure of that water can be somewhat characterized to find its maximum accumulation mode, and that's why you tend to have these bimodal distributions, which you can see right up there, okay? So you have the bimodal distributions, and the bimodal distributions is you have large particles which are broken off of the bulk particle. Those are the large particles, and those could be anywhere between like 1 micron and 50 microns, all right, depending on the material. And then you have the smaller distribution, which is components of that which have had so much energy that they've then been decreased below their Kelvin barrier, in which case they rapidly aerosolize and then gradually, or in some cases, on our time scale very quickly, but in the time scale of aerosols, somewhat gradually, recombine and connect like magnets. Imagine you have a table full of magnets that are very carefully set up, and you roll a ball bearing through, you're going to see all kinds of crazy magnetic action. That's something of what happens when particles tend to aggregate. Is there's so much available surface energy that it's like when you're at the school dance, okay, and the teacher's like, okay, boys and girls each go on one side of the gym, and then the boys and girls both go on one side of the gym, and she said, okay, now we're going to dance. Each one of you has to walk over to the other side and pick up a partner. Okay, so the dielectric, in this case, it's not just dielectric, it's also an entropy gradient, of having one of those girls come across and ask a boy to dance, and one of those boys going across and ask a girl to dance is very high when none of them do it, okay? But as soon as more of them start coming across, and there's girls coming across and boys coming across and everybody's asking to dance, eventually there's like the density of people asking each other to dance peaks, and then it starts decreasing again. So it starts small, and what do you have? You have a Gaussian distribution. Okay, so with that Gaussian distribution inside of each one of those modes, the small mode is from these small aerosolized particles aggregating together. Okay, so when you have a more, what happened? Oh, there we go. Okay, when you have a more forceful sneeze, that's when you start getting the aerosolization, because the particles are moving then so fast that the viscosity of the air creates essentially like a little shock wave for these droplets, and they break apart. They aerosolize even more. They sometimes recombine. They sometimes stay little. They sometimes get very little and then get a little bit larger. There's all kinds of crazy stuff that happens with them. But you have aerosolization. Okay. So now, and then that, by the way, this problem, so I've gone up in complexities. So I started with a relatively simple complexity, which was just, which was this one, which was just normal speech or normal breathing, to then 2 people breathing, 2 people speech, and then coughing, and then sneezing, and then finally, okay, so there we go. Okay, this is really complicated. Doing the math and physics behind this is really, really heavy. I mean, you can get some basic approximations from a thermodynamic perspective, but genuinely being able to cover the fate of aerosols in an applied way, in an applied theory way, without using COMSOL, for instance, and actually having a closed form with an actual equation that describes it, really, really complicated. This could be a life's work for one person. I mean, it could take you a lifetime to figure it out. Okay, and people have, not for every system, but for a lot of systems, people have been able to take the Navier-Stokes equation and then take the pieces out that they need and add in some more pieces and actually come up with a closed form using Navier-Stokes for some remarkably complicated systems. Very, very smart people that are able to do this. Okay, but it's very, very difficult, incredibly difficult. And coming up ab initio from thermodynamics and kinematics things is somewhat simpler on one side, but it adds to a lot of the the industry runs on Navier-Stokes, so it doesn't make it as approachable. You've got to be kind of a Navier-Stokes expert to understand it if you're not taking a thermodynamics and kinematics approach to these, or entropic change as well. Okay, and then finally, now what's missing here? Okay, what's missing here is that they're not facing each other. They're facing one direction. And the reason that's missing is because somebody coughing and sneezing on each other with high velocity at close distance pushes the bounds of being able to describe the fluid dynamics of this. Okay. All right. So they're all facing the same direction. So you can take one and you can just do some additive work on it, but that's tractable at least. Okay. So that's where it comes. That's where all of these things have to do with. You can run these in the other direction if you were to run this video backwards. Okay, so imagine taking this video and literally running it backwards. Let's run it backwards. That is essentially the same process with some changes, but it's essentially the same process. If you run this video backwards, instead of liquid coming from the lungs, liquid coming from the nose, liquid coming from the mouth, it's the opposite. It's air pollution, yeah? It's particulates coming from smokestacks and then entering our lungs, okay? Because in that case, we're taking a often highly linear flow, and in many cases, it remains highly linear up through the time we breathe it in. So the idea is, and then of course you can go the other direction. Things can get aerosolized. Things can be in highly turbulent, high Reynolds number systems. They can be in systems that are fully turbulent and essentially chaotic and non-qualifiable. I guess you'd say from an aerosol perspective, they are ill-posed problems. They are potentially solvable and fixable, but it's hard to figure them out. So if you run this video backwards, you would then see this entire problem from the air pollution perspective. It's essentially the same thing. The difference is, in the case of people, it's kind of more complicated, because in the case of air pollution, you have a source and you have a sink. You have a smokestack. You have the stuff coming out of the smokestack, flying around, yeah. And you have the person who then breathes in this horrible material from the smokestack. But we know that this is the person we want to protect. This doesn't need any protection. This is a smokestack. It's made of bricks and mortar and concrete. But in real life, I don't have anything else on my desk. It has to be this transformer. Hello, how are you? Oh, I'm okay. Thanks, man. All right. So in this case, it's much more complicated, because this person is a source and a sink, and this person is a source and a sink. And this person can be damaged by stuff coming from this person, and this person can be damaged for stuff coming by this person. And so while it suggests a symmetry, unfortunately, they almost never cough at the same time. This guy coughs, and then someone later, this guy coughs, and this guy says some words, and then this guy says some words. So if you're looking for a symmetry, it's tough, because this one's breathing in at a different rate, and this one's not breathing in at the same rate that's coughing and sneezing, and this one's breathing while this one's talking. And yes, there are definitely some symmetries there, and are definitely necessary to be able to manage these problems. But from a physics side of view, they're just not terribly useful. And so much of the understanding of this has to be based on the experiment of just seeing where these distributions go, because at this point, it's almost the need for understanding communicable diseases is more apparent now than it's been before. Um, Probably because of the coronavirus, but also because, you know, I don't know why. I can't figure that out. I'm not even going to try. All I know is if we can understand the transmission of course, say this community acquired pneumonia to this person and this community acquired pneumonia to this person, there's a potential to
relax, calm down now, don't stress, take it easy.
wait, why did I put it there? The microphone's here. All right. There's an opportunity to make these applied theories help in the understanding of air pollution. Yeah, that's what I think. It's useful because 4.1 million people die of air pollution every year, and it would also be really good in hospitals if people could have some means of not catching hospital-acquired infections, because that's a massive amount of death toll, hospital-acquired infections, and it needs to be controlled. It's probably almost as high as air pollution. And it's nothing on the hospital. They're doing great. It's just that if there's a way of fixing this thing, of understanding it through applied theory, it seems like there's a good opportunity. And understanding why this problem is so complicated is something I hope I've accomplished over the last 20 minutes. All of these different things, all these crazy tangents I've gone into ultimately have to be accounted for in that formula. It has to be. Because if it's not, when you put it on your benchtop test and you're actually grabbing data, your data won't fit the model. So you need it all. It's just a necessary it's a necessary component of understanding this stuff. We can just put all the data we want. We can do all the computer modeling we want. But if we don't understand what's fundamentally happening on a at least linear Newtonian level, I'm not even talking nonlinear, just a basic linear Newtonian level, first approximation, then I think we're playing with fire. We have to know what's going on, and all of these things have to be accounted for. The aerosols, the linear, the nonlinear, the turbulent, the transitional, the laminar, the shape of the barrier with non-constrained fields of flow, the change of potential of the flow, the change in entropy of the before the sneeze and after the sneeze, and before the speech and after the speech. All of this stuff has to be accounted for. I don't know of any other way of doing it. So, okay. Thank you very much. Wait, where's my little guy? Hey. Come on, speak. Speak! Speak!